Hi class, in this lecture I would like to talk about simplex algorithm, an essential tool for solving linear programming problem. Of course, there is another tool called interior point method, but it is difficult to use comparing to the simplex algorithm. I will divide it simplex algorithm into two parts. This is the part 1. The key of this lesson is to know the mechanism of the simplex algorithm. Remember, when we talk about the select variable part, we can do a sequence of the pivoting to get solution for the problem, but actually we don't know which one is better, or we don't know if this solution reach optimal solution. So if we generate a sequence of pivoting, we can provide the objective function value as a guideline for the pivoting. We have the information to judge if the solution reach the optimal solution or not. I use the same example, Farmer Jones case. The objective is maximize revenue, which is the z equals to 80 times x1 plus 60 times x2. Here x1 means the number of acres of wheat. x2 is the number of acres for corn. And the three constraints are land constraint, labor day constraint, and the cost constraint, respectively. Of course, x1 and x2 must be larger or equal than 0. The first step is we try to restate the problem with the select variable for 3 different constraints, and all variables of objective function we need move from the right hand side to the left hand side, like this one. And for the constraint, we try to make the inequality become equality equation with the select variable s1, s2, and x3. And the second step, we try to build a simplex table. And we move the objective function into the bottom. Okay, so for the x1, x2, s1, s2, x3, and z are variable. We just record its coefficient. And for the first land constraint, the coefficient is 1, 1, 1, 0, 0, 0. And the right hand side is 100. And for the labor day, coefficient is 2, 1, 0, 1, 0, 0, and right hand side is 150. And for the cost constraint, the coefficient is 5, 10, 0, 0, 1, 0, and right hand side value is 800. As for the objective function, the coefficient is minus 80, minus 60, 0, 0, 0, 1, 0. Okay, and you will see here if the minus sign here provides that it has a room for increase the revenue if we increase the x1 or x2. Until there is no improvement, such as the value becomes 0, then there is no chance to increase the objective value by the variable. So This one provides a very good guideline to do the pivoting and evaluate the result if it is reach the optimal or not. So there are 6 rules for simplex algorithm for rule 1. Rule 1, try to obtain the initial basic solution by setting each select variable equal to the corresponding resource and setting the other variables equal to 0. So this is the basic idea to set up initial value for select. Okay, and now because the resource and the select variable are equal, that means actually no resource used. So we try to decrease the value of the select and increase the value of the x1 and x2. Here are some examples about the terminology of the variable. Subsequent solutions are obtained by a succession of pivoting operations to make positive or variable. That positive is called entering variable. Okay? And the one variable becomes 0, we call it leaving variable. Okay, so for each time we have basis. For example, in the first basis is S1, S2, and S3, and we try to let X1 or X2 into the basis, become a basic solution. If one becomes a basic solution, then we need to leave out a slack, become non-basic solution. Okay, that's the concept of entering and leaving. But how can we determine which one is entering, which one is leaving, is according to the rule 2. Rule 2 choose the entering variable from among those having negative coefficients in the objective row, such as like here, right? This is the objective function. We have 2 possibilities for x1 and or x2 as an entering variable. Usually the one having the most negative coefficient is selected. Why is that? Okay, we can see the original equation. Okay, here. If we increase 1 unit in objective function, then you will know the revenue increase 80. But we choose x2, increase 1 unit, the objective only increase 60. For the negative value, so this one is the most negative value for x1. So in this way, we will find very efficient way to reach the optimal solution. In the case of time means if these two negative value the same, we can either choose one of it as the entering variable. Selection of the leaving variable depends upon the replacement quantities. Okay, for the entering, we just see the most negative value, but for the leaving variable, we need to calculate the replacement quantities. So this one is the non-negative quotients that can be formed by dividing the resource by a positive entry in the column of the entry variable. We don't consider the negative value, we only consider the positive value. Note that only a row leaving a positive entry in the column of entering variable will produce replacement quantity. That means we don't need to consider other column. For example, if we choose the x1 column here, we don't need to consider other column. We only consider this column to calculate replacement quantity. Rule 3. Rule 3 identifies the living variable by examining the replacement quantities. This rule also maintains non-negativity by selecting the value of entering variable from among the replacement quantity so that no variable will be negative in the next solution. Okay, so once you finish the replacement quantity calculation, you compare those calculations and choose the smallest one to determine the living variable. And once you determine the entering and the living variable, you can determine the previous cell of the table. This is the rule 3. When you finish the rule 3, actually you make one table to the other table. But should we terminate the calculation or not? We still need to do the judgment. There are some things, for example, like if this problem is unbounded problem, or we reach the optimal, or we have multiple optimal solution exist. Okay, so this is need to depends on other rules. So rule 4 is try to judge the upper bound. There is no upper bound on the objective function when one column has entire non-positive coefficient above the negative coefficient in the objective row. So if you want to judge there is unbounded, then you need to depend on the rule 4. The absence of the upper bound is detected when applying rule 3, while no replacement quantity can be found. There is no upper bound. Okay, so this is very important when you calculate the replacement quantities. And also, if there are two variables only, you can use geometrically to see what happened for your problem. The replacement quantity represents points where increase the value of the entering variable is limited by constraint. Where no replacement quantity exists, the value of the variable can be increased without bound. Okay. So that means when x is increased, then the objective is increased. There is no bound for constraint. Rule 5. Rule 5 is the solution is optimum when all entries in the objective row are non-negative. So it needs to termination because it already reached the optimal solution. And rule 6. If all basic variables are positive, an optimal solution is not unique if in the optimum table a 0 occurs in the objective row in a column corresponding to a non-basic variable and including a positive entry. The second optimum basic solution with the same optimum objective function value can be obtained by pivoting in column identified by rule 6. You will consider the complications arising from a basic variable being 0 in the solution called the generated solution. It seems that the objective value will be the same and the same and the same. Okay. This is the flowchart of the simplex algorithm. The first one is we insert. Okay, we insert the select variable and generate initial solution, which is rule 1. And we will judge if it is reach optimum or not according to the rule 5. If yes, we go to the rule 6 to judge unique or not. If yes, then stop. Okay. If no, we try to determine other solution, then stop. Okay. And if the initial solution is not optimal, then we try to do the pivoting by choosing entering variable, which is rule 2, and determine replacement quantity to find if we can determine leaving variable or not. If the answer is yes, then we do the pivoting and continue. If we cannot find the replacement quantities, then the solution is unbounded, then we stop. Okay, so that's the relation between rule 1 to rule 6. Next, I will give the Farmer Jones example from the start to the end. Okay, so the first step is try to insert select variable and generate initial solution. Okay, so when we got the first table for tabular here, okay, we can see for the basis is these three, right? So we can see S1 is 100, S2 is 150, S3 is 80. For the X1 and X2, because it is non-basic variable, then the value is 0. So the initial solution is X1 equals to 0, X2 equals to 0, S1 equals to 100, X2 equals to 150, and S3 equals to 800. Z is equal to 0. Okay? So, let's continue. If this one is optimal or not, definitely it's not. Because if it is reach optimum, according to the rule 5, all the entry in the objective row should be non-negative. But we can find minus 80 here, minus 60 here. So this solution is not optimal solution. Then we continue to try to find the pivoting point, which means we need to determine the entering variable and the leaving variable. First, we need to determine the entering variable according to the rule 2. Okay, and the minus 80 here and the 60 here, we choose the most negative value for the entering. So the column will be the blue column here. Okay, and the next one is we try to do the replacement quantity to determine the leaving variable. Okay, so we use 100 divided by 1, 150 divided by 2, and 800 divided by the 5. Okay, and how we determine the leaving variable, we choose the smallest value of all, right? So the 75 is the smallest value among the 175 and 160. Okay, so we can determine the pivot is here. Okay, then we can, according to this point, to do the pivoting for the next solution. Okay, so first one, we try to let this row, the coefficient of the pivoting number become 1. So we divided 2 for entire row, so it will become the 1, 1 half 0 1 half 0 0 75, right? And then we try to make other row, like the first row and the second row here. At the same column should become 0, right? Become 0. So we can times -1 for all column, right? All column. Then add it to the first column. And times -5, add it in the third column, right? And then we times what? Times 80, right? Times 80 to that, this number becomes 0. Okay, if we do so, we can get the second simplex tabular like this. Okay, and you can see now the objective function value become 6,000 instead of 0, right? So this one is better than the last solution. Okay, so in this way we choose the basis is x1, s1, and s3, right? So s1 is 25 here, x1 is 75 is here, right? And s3 is 425 is here, right? This is for basic variable, and for non-basic x2 and s2 becomes 0. Okay, so the basis here is x1, s1, and s3. If you use the figure to show what happened in this case, we can see originally x1 equals to 0, x2 equals to 0, right? And now we shift from this point to this point, right? Okay, so if this one is optimal solution or not, okay? So we need to check, according to rule 5, we need to check all of the value in the objective function row here. If there is still negative value for increase the objective function value. The answer is yes here, right? We have -20 here, so we still have the chance increase the objective function value. Okay, so this one is not optimal. So we need to determine the entering variable and the leaving variable for the next table. Okay, so according to the rule 1, we need to determine the entering variable, which is most negative value. There's only one, right? -20. So x2 will be the entering variable, and we do the replacement quantity. Okay, so we use the 25 divided by 1/2, 75 divided by 1/2, and 425 divided by 15/2. Okay, so we got this number is 50, 150, and 160 divided by 3. So 50 is the smallest number, which means we will choose this one. Okay, we will choose the S1 as a leaving variable. Okay, so this one will be the pivoting point. Okay, so the first one, we need to make this number become 1, because here 1/2 we need to become 1. So entire row we times 2, right? So here become the 0, here become 1, here become 2, here become -1, 0, 0, 50, right? And the next, we try to make this number become 0, and this number becomes 0, and this number becomes 0. Okay, so we can times this one, this row, new row, times minus 1/2, and for this one times minus 50 divided by 2, and this one times 20. Okay, and we will get the new results for this one table. Okay, so the new bases are x1 here, right? x2 here, right? And s3. Okay, so x1 is 50, s2 is 50, and s3 is 50. Okay, and for s1 and s2 now is non-basic, which is 0. Okay, so finally we need to determine if this one is optimal or not. We can find all of the value in the last row are positive. Okay, which means according to the rule 5, it reached the optimum. Then we need to judge if it's unique or not. Okay, so we see none of the entry corresponding to non-basic x1 and s2. So here, right? In the objective function are 0. Okay, so these two are not 0, it's positive value. So that means it's a unique solution. Okay, so we stop. Finally, we find the solution. Okay, and for the table, you will observe that, okay, we can see in Z column, okay, from the very beginning, Z column, okay, all Z column, okay, start from here. Oh, maybe I changed the color. Okay, Z column 0, 0, 0, 1. Okay, 0, 0, 0, 1. 0, 0, 0, 1. Okay, 0, 0, 0, 1. 0, 0, 0, 1. Okay. Okay. No matter which table, you will find this column. All of the values are the same, 0, 0, 0, 1, right? Because actually in the constraint, there is no coefficient, which means the coefficient are 0, right? So it doesn't matter if you have this column or not. So sometimes we will delete this column. Okay? We don't have this column, and the table will become like this, right? Okay. So this is the simplex algorithm from rule 1 to rule 6, the example. Hope you can find the example and follow the flow charts and do the exercise. Actually, I will give you an assignment to do this. So do the homework, then you will familiar with the basic flow of the simplex algorithm. So see you. Bye bye.